Right. So let's see. Okay, let's begin. So in the previous class, we discussed about the wave-particle duality of stuffs. We said that light can behave as a wave and particle, and electron can also behave as a wave and particle. In fact, everything that you see around can behave as a wave and particle, including we ourselves. It's just that um, for us, for big materials, the particle property dominates over wave property. Especially if the mass increases, then the particle property dominates. For small stuffs, where the mass is very small, like electrons, the wave property dominates. Even bacteria and germs, which are very small, we can see some wave property for those stuffs. So, so that means since uh, particle can be very strange, and we must need some new kind of equations in order to understand them. We know that Newton's law of mechanics, it helps us to understand the motion of particles. If you throw a particle, uh, let's say it goes in a projectile, and you can use Newton's formula to understand that how it propagates. But you cannot use the same stuff here because Newton thinks that everything is a particle. If something is new here, we need new equations. So where can I begin with? We'll start with the wave equation first, general wave equation. And then we'll see that how we are going to modify this general wave equation to come to a new kind of equations that can describe not only waves, but also particles. So let us see how we will begin. A general wave equation looks like the following. The general wave equation for any wave, for a mechanical wave like a sound wave or even a light wave, um, everything can be explained by this wave equation. It follows this particular equation. So how can I solve it? One way of solving it is to first see that what these guys trying to tell us. You see, this symbol, psi, we have to solve this psi from these equations. Now, this equation tells that the value of psi would be such that if you take a space derivative of psi twice, it will be same as the original psi with a multiplication constant k square. So for now, let us assume that this k is just 1 so that it becomes even simpler. Okay, if it is just 1, you can just imagine that it is d square psi divided by dx square is equal to psi. So as I said, the psi must be something so that if you take the derivative of psi twice, it becomes the original psi. Okay, so I know that if I take the derivative of x with respect to x, what is it? Just 1. If I take the derivative of xn with respect to x, what does it become? Right. So this means the psi cannot be x or x to the power n, right? Because after you take the derivative or after you take the second derivative, let's say, if I take the second derivative of dx to the power n divided by dx square, it will be like n multiplied by n minus 1 x to the power n minus 2, right? This is how it should look like. So it's clear that the psi cannot take a form of x to the power n. Okay. In fact, we know that if I take a derivative of something, it will of course change its form. Can you think of any expression which after you take the derivative, it remains the same? E to the power x. That is the thing. So if you take e to the power x and do a derivative, no matter how many times you do the derivative, it could be twice, thrice, it will always remain same. Okay. In fact, this is the very definition of e to the power x. Okay. The definition of exponential to the power x means the function which does not change its form even after derivations. Okay. So maybe e to the power x would be a solution for this guy. There is some more. Look at that. It says it's not actually the equation that tells you. Let's say I have an equation like this, okay? D psi dx equal to psi. Then I would say that yes, e to the power x is a solution for that. But this equation, the actual wave equation, it says it's not d psi dx, but d square psi dx square is equal to psi. So it says that when you take the second derivative, it becomes equal to the previous equation, original equations. So not only the first derivative. Can you think of any expression which after you take the second derivative, it becomes equal to the previous case? Cosine. So if you take sine and take a first derivative, it becomes cosine. Take another derivative, it becomes sine again, right? Same thing about cosine as well. So we now eventually understand that maybe we can take both sine and cosine as a solution. So let's try this. Let's say psi is equal to a cosine kx plus b sine kx. Okay. If you plug in this expression into the wave equation, you will see that it satisfies. Because both sine and cosine, if you take the derivative twice, it becomes equal to the previous expression. Okay. So this is how I understand that this is the wave equations. And sine and cosine, how does it look like? It's just look like this. So if I have, let's say, a guitar string, the oscillations in the guitar string will look like a wave, and this wave could be either sine or it could be cosine. Okay, or a combination of them. Could be a combination of sine and cosine. Everyone follows? Okay. So now we know that how the wave equation can be solved and how it will look like after solving. Now, the second thing is that, let's say, in addition to the wave equation, we also have some boundary conditions. And the boundary condition says that the wave must be zero at each of the terminals of your system. So let's say we're talking about a guitar string. So guitar string only oscillates in between the two terminals. But when you go to the very right-hand side or very left-hand side terminal, your wave must be zero. So those are called the boundary conditions. Once you apply those boundary conditions, then you will see that the value of k that I wrote here, it cannot be arbitrary. The value of k must be something very specific. So what is k? K is called the wave number. So it means, you know what is frequency, right? And you know what is wavelength. So k means how many waves, how many peaks of waves are there in a given unit length. Okay, so let us say this is 2 meter, a guitar string of 2 meter length. Of course, it's 2 meter is very long, but let's say this is 2 meter. Then I know my wavelength from this picture is actually 2 meter, right? And I know my k is must be there is one wave in 2-meter length. So K must be 1 divided by 2 meter. Okay, that is K. And then they multiply the entire stuff with 360 degree to convert it to phase. Okay, but that's basically it. K means the wave number. Give me 1 second. I'll check whether we are being recorded. All right. So with the boundary condition, that means the psi must be 0 at the two terminals. If you apply this boundary condition, you will see that the value of K can only be some very specific value. And this value can be written as, I'll write it here. This value can be K is equal to, let's say, I forgot already, 2 pi L by lambda. Okay. And actually, it is this. KL is equal to 2 pi n. And from there, we can write that lambda is equal to twice L by n. Okay, where n is some integer number. N can be 1, 2, 3, and any integer number. Why this integer number? It's because you understand that once we say that it has some specific boundary condition, wave must be 0 at this side or at the very other side. So these waves cannot be arbitrary. It must take some specific form. Okay. So it can take either this form or blah, 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 right? Out of all these 4 configurations, which configuration would have the longest wavelength? The top one or the bottom one? The top one. This has the longest wavelength. Okay. And that longest wavelength is actually twice of L, where L is the dimensions of the cavity. So if you take a guitar string which has a length of L, the minimum of, not the minimum, the maximum wavelength can be twice of the guitar string's length. Okay, it cannot be anything smaller. Okay, so you understand that once we look at the wave equation, once we look at the boundary conditions, we know that our lambda cannot be any arbitrary value. It must have some lower limit of value. And also, lambda cannot be any continuous value. It has some discrete values. Okay, either lambda is twice L or lambda is twice L by 2 or twice L by 3, something like that. Okay, so it will always follow twice L by n. Okay, it's always discrete. Okay, so that is a very important discussion here, because in the next slide, we will see that how it is going to impact our electrons. Remember that so far, we just talked about the waves. There is no particle at all, at least for now. But now we will see that where does the particle will come into play. Okay. So we discussed previously that people discovered through Compton's effect, Compton's law, where they threw a electron with a light and looked at the scattered particles. And they have seen that light is changing their wavelength after scattering. So based on those experimental phenomena, they came up with the idea that maybe the momentum of light has something to do with its wavelength. And they proposed this formula, P is equal to h divided by lambda, where h is a Planck's constant and lambda is the wavelength. So using this simple law, and they just plugged that into previous wave equation. Okay, so what did they get? They get the following. Remember that we started with the wave equation, and the wave equation looks like the following. D square psi divided by dx square is equal to minus k square psi. And now we want to replace the value of k is the wave number, with the formula of the following. K is equal to twice pi divided by lambda. And from wave particle duality, we know that lambda also can be replaced by momentum. And momentum is, let me write it this way, twice pi 1 by lambda can be written as h cut by p. P is the momentum. Remember, momentum is mass multiplied by velocity, right? And then we can also proceed further. We can say that, look, momentum p, which is actually mass multiplied by velocity, it has a relation with the energy of the particle. How? E is equal to half mv square, right? This is the kinetic energy. And the potential energy, let's say V. So we can say that the kinetic energy, Ke, can be written as P squared divided by twice m, where P is the momentum, m is the mass, okay? So if you use all this very simple law, which is well known to us from Newton's law of equations, like this guy is all known from Newton's law of equations. The only new stuffs that we know is this guy. P is equal to h cut by lambda. Everything else was actually known. The wave equation was known. The Newton's equation was known. Now we're just going to combine all of them together. So when they combine, they get up to the very final equations, which says that the second derivative of psi with respect to position is equal to E minus V multiplied by the psi itself. And it has some other constant which depends on the mass. So this is the new equation that is going to describe both the particle and the wave, okay? Because it contains the wave equation itself. It also contains Newton's law of equations that provides this relation between energy and the momentum and mass of a stuff. So this is the final equation that people talk about a lot in quantum mechanics. It's called schrodinger equations, okay? So let me tell one more time that what does this different part means, and what is the wave and particle is mixed up here. So wave is represented by this psi, okay? We talked about it, that psi can take a form of sin x or cosine x. So it's clearly a wave. Now, where is the particle? The particle actually is here. M, remember that when you talk about a wave, there is no question about mass. But now we bring both mass and particle together through using these equations. And now we have a mass of a wave. Now that becomes very interesting. What are the rest of the stuffs? E is the energy, total energy of a particle. And V is the potential energy of the particle. So if you solve these equations, solve the value of psi, you will get something which represents both particle and the wave. So in our next step, we will try to see that how the solution would look like. Okay. So few things before we proceed on solving this equation. First of all, we need to understand that what is the that potential energy that we talked about. Remember in the previous slide, we talked about the potential energy, Vx, and the total energy, E. Okay, so now you need to understand that what is the potential energy for electrons. Okay. Before we answer that, let me ask you this question. You know what is potential energy, right? So if I pull up a stuff from ground it will gain some potential energy, right? And it depends on how high I'm pulling it up, right? What is the distance between the ground and this stuff? Okay. There are also some other example of potential energy. For instance, if you take a spring and attach this spring with a mass and try to move the mass around, then because of the distortion of the spring, it will gain some potential energies, right? Okay. So let us see whether we know that what is the potential energy for a spring mass system. Do you guys know that if I pull a string with a mass, let's say I pull the string by an amount of x, how much force do I need to exert in order to pull the string by an amount of x? So let's say this is a, you need the spring constant, right? What else do you need? So let's say this is a spring. Let's say the spring constant is a k, okay? And let's say you pull the spring by an amount of x. Do you know that there is a relation between the force and the spring constant and the displacement of x? Say it again. Kx, right? So that's the force, right? Once you get the force, then you can find out what is the potential of the mass. So if you pull the spring, of course, it will gain some potential so that when you release it, it will come back to the previous position. So how do you find out the potential? Do you know there is a way to find out? It's always, the potential energy is always f dx, integration of f dx, okay? So if I do these integrations, what do I get? Half of kx square, okay? Plus a constant. So that's the potential energy for a spring mass system. And how it will look like? If I try to draw, let's say this is x, and I'm trying to draw the potential. So this is a parabola, right? Kx square is a parabola. Any question up to this point? Yeah, you're correct. This is a minus sign. For now, I'm just looking at the shape of it, and that's why I'm ignoring it. But you're absolutely correct. It's a minus sign. Yes. Thank you so much. So the potential energy looks like a parabola, half kx square. So that means it will look like this. Okay. So this means to look at the potential energy and let's try to understand. So this potential energy, it says that if you take a mass further away from the equilibrium, let's say you pull it to the x directions and you release it, it will try to go back to the equilibrium position again. I mean, it will of course oscillate back and forth, but eventually it will try to become rest at the equilibrium position where the potential energy is minimum, right? So any object, it always try to minimize its potential energy, right? All right. How about electron and nucleus? Let's see if we can find a potential energy for electron and nucleus system. Instead of a spring, let's say we have a nucleus with protons and electrons. So the protons has positive charge, electron has negative charge. In order to find out the potential, we first need to find out the force between them. And the force can be found out by using Coulomb's law, which says force is equal to the multiplication of charge of electron and the multiplication of charge of proton divided by the distance, which is r, right? So from this equation, we can find out the potential energy, which is simply the integration of f dr. So if I do the integration, how it would look like? It would look like, I think this. So ignore the positive and negative. Just look at the magnitude of the expression. So it will look like V is equal to K multiplied by the charge of the electron and protons divided by 1 over r square, right? So how it would look like if I try to draw this function? Let's erase this. Tell me, you guide me. How should I draw it? Ignore the sign, okay, plus minus sign. Just tell me that if I try to draw the position R versus the potential energy V, how it would look like? Let's start from 0. If R is 0, what is potential energy? It should be negative infinity, right? If R is 0, it should be negative infinity. And if R is infinity, it becomes 0, right? So we can draw like this. Let's say this is, let us say this is your position coordinate R, and the y-axis is your potential. Then I know that when R is 0, then the corresponding potential energy is negative infinity. And when R is infinity, then potential energy is 0. So it would look like the following. Okay, so look at that. When R goes to 0, the potential energy goes to negative infinity. When R goes to infinity, potential energy goes to 0. Okay, so this is how it will look like. Okay, although it doesn't look like parabola, but the main idea remains same, that if you try to pull the electron away from the nucleus, if you try to pull the electron, let's say the nucleus is here, okay, and you are trying to pull the electron, if you release it, the electron will go back to the nucleus because the potential energy is minimum here. Okay, it will try to fall back to the well. So that was the original dilemma. We started with this dilemma that electron cannot stay a little bit away from the nucleus. It is bound to go back to the nucleus and just collapse. But now we have some understanding that electron is also a particle. So if electron is a particle, then how it is going, electron is a wave, how this wave nature of electron is going to help solve this problem. Let us see. So since the actual potential energy profile looks a little bit um, not so simple, like I showed you the actual potential profile, which goes to negative infinity and becomes 0. Uh, in order to simplify our discussion, I would redraw the potential energy by some simple modifications. Let's say this is an approximation, okay? So instead of having something like this, which goes negative infinity, I draw a potential which is actually 0 in the middle and becomes infinity after some distance. So let us say this is the length of A, and as long as you are within the length of A, your potential energy is the minimum, which is 0. And the moment you try to go outside of this region A, your potential energy will become infinity. Okay, so this is also infinity. Okay, remember that we are just trying to simplify the potential energy profile so that we can easily solve the wave equations. Okay, that was the original potential well. We just modified it a little bit so that it becomes simplified. Okay, so the reason why we made it simplified is because now it just looks like a cavity. Okay, it's a cavity which is bounded by a hard wall. So nothing can go out of that cavity. Okay. If nothing can go out of the cavity, we discussed a moment ago, then the wave inside the cavity, it must be taking some specific value. Either it will look like this, or it will look like this, or it will look like this. Okay, there are some very few specific value. The least value of the wavelength is lambda is equal to twice A, right? So if lambda has a minimal value, we know that lambda also relates to the energy. You remember this? I erased it, but here is again the equations between lambda and the energy. How do I write this? The energy is p square by twice m, and if you plug that p with h by lambda, you will get energy is equal to h divided by lambda, take the square and divide them by twice m. And we know that lambda has a minimal value, which is written as nh divided by twice a. Take the square, divide them by twice of m. So now we know that n is actually some integer value, starts from 1. It can take 2, 3, 4, any integer number, but it cannot be less than 1. So if n cannot be less than 1, that means the energy must have some lower limit of value, right? So if I put n equal to 1, you will see that the energy, the minimum energy of an electron must be h squared divided by twice a whole square divided by twice m. That is the minimum energy of an electron. Yes. Say it one more time. Yeah. Yeah, that's true. That's true. Yeah. Actually, you're right. N can be negative. Yes, but that doesn't make any difference because we are just taking the n square, right? You are absolutely right. N can be negative. So you know that since n can be as low as 1 or minus 1, that means energy must have some lower limit, and this lower limit is defined by h cut square divided by twice s square. So now you go back to this question one more time. I said that we have a potential well. The potential well is like this, that in between this region of A, the potential is 0. Outside of this region A, the potential is infinite. So if you take a particle, if you push the particle into the cavity, what do you expect the particle to be? It should go all the way until it reaches the 0 potential, right? But now I say that the particle is not only a particle, but also a wave. So it means when it tries to go down, it must make sure the wave has a minimum limit, okay? Because the wave has a minimum limit, the lambda has a minimum limit, the energy must have a minimum limit. It cannot be 0. You see this? Let me know if everyone follows. In conventional scenario, when we talk about very large object, it is absolutely clear that if you throw a particle into a well, it will reach all the way to the bottom where the potential energy is 0. But for a microscopic particle, when the mass is very small, it has a wave behavior. It will not reach all the way to the bottom. It will actually get stuck somewhere, because if you reach all the way to the bottom, your energy is 0. But we just proved that because lambda cannot be 0, lambda must have some particular value. That means energy also must have some particular value, particular minimum value. Okay, so this is why this is the minimum energy that a particle can have. If you push it into a well, it will not reach all the way to the bottom. So it's like this: if you push an electron into this hole, it will keep falling until it reaches that minimum electron's energy, and it will be stuck there. Yes. Yes, exactly. So let's just talk about the minimum electron energy. Minimum electron energy corresponds to minimum maximum wavelength. Okay, when the wavelength is bigger, then the energy is the minimum, and we know that the wavelength cannot be arbitrarily bigger. Okay, the maximum value of the wavelength can be twice of a. Okay, so it means that if you push an electron into the well, it will keep falling down until it reaches that minimum value. Okay, so it will be stuck there. It's a really, really peculiar phenomenon. Like nobody would know that this is true, right? And this is the reason why in an atom, if you pull an electron from the nucleus and release it, it will keep falling down, like it will keep going closer to the nucleus until it reaches a point where the energy cannot be any lower. Okay, so that's why it will not go all the way to the bottom. Here, bottom means all the way to the nucleus. It will stay somewhere where it cannot go any closer. Okay, why it cannot go any closer? Because if it tries to go any closer, then its wavelength has to be even bigger. Okay, but it cannot be any bigger because it is bound by a potential well. Okay, does everyone follow to this point? It might take some time to wrap around, and believe me, this is not a simple idea. It is a very complex idea, and it's a head twisting idea, and people fought over it. Okay, the best of the best scientists, they fought over it. They thought that this may not be true, but eventually it turns out that this is the true case. Okay, in fact, this is the only way by which one can explain that why an atom exists, why electron does not just collapse with the protons. Okay, it's because the wave nature of electron, it kicks in, and because the wavelength cannot be bigger than a certain value, it must have some certain energy which cannot be anything smaller, and that's why it doesn't go all the way to the nucleus. Everyone follows to this point? All right. So let us see what else we can talk about. So now we talked about the most strangest part, and I think we started this conundrum a couple of lectures ago when we say that why an atom is stable. And only up to this point we get to an answer that an atom is stable, an electron does not fall into nucleus. It's because the electron has a wave property, and the wave in a cavity, the wave cannot be anything bigger a certain value. Okay. So now the other question is, okay, let us say that electron is a wave, and we know that wave is not located into a particular place. A wave is expanded, right? So let's say um, let's say that, okay, I agree that electron is a wave. So let's say an electron exists here, all the way from here to there. Now let's say that, let's just imagine that we are also microscopic people. So we somehow are able to stand here, and let's say one of my body is also able to stand here. And I say that the electron, it has a wave going from here to all the way up to there. So does it mean that both of us will see the electron? Shall I repeat the question? So I said the electron is a wave. That means electron does not stay in a particular local position. It's actually spreaded around it. Okay. So if electron is a spreaded object, and if I take me and my body and put me and my body into two different places, will both of us be able to see the electron in my own position? Because if both me and my body, both of them are able to see electron in their own position, that means we're actually double counting an electron, right? Right. So then the other big idea came in. It said that, you know what? You can see, you and your body, if you have two different positions, you can see the electron, but not at the same time. Okay. Either you will see it or your body will see it. Okay. So how do I know that when do I see it and when my body will see it? And the way we know is the following. Let's say I'm talking about electron in a cavity, and my electron has a wave like this. Remember, this is the shape of the shy of electron, and this corresponds to the maximum wavelength and minimum energy. So if I put myself here and my body here, let's say my name is A, my body's name is B, then A and B will be able to see electron, but not at the same time. Then how do I know that at what time do I see the electron and what time my body will see the electron? So then people say that it is actually probabilistic. It means sometime you will see these electron at your position, and sometime your body will see the electron at their position. And the probability depends on the square of the magnitude of psi. So it says that if you take psi and take a square of it, it becomes probably this. Let's say this is the square of psi. Okay. So psi square actually tells you that what is the probability of seeing a particle at a given position x. Okay. So from this picture, it is clear that the probability of seeing the electron would be maximum if you stand right at the center of it. Okay. If you try to go to the left or to the right, the probability of seeing the electron would be less. Okay. Let's look into another scenario where electron does not have the maximum wavelength, but electron has a wavelength that looks like this. So this is the condition, and the electron's wavelength looks like this. Remember, this is also a solution. Okay. Now here, if you take the square of this guy, it will look like this. So this is psi. Remember, this is psi of x, and this is psi square of x. Right? If you take the square, then everything becomes positive. So if you stand at this position, and if your body stand at this position, then both of you and your body will see the electron with the same probability. Okay, let's say you see the electron with 50% probability, your body will also see the electron with 50% probability. Say it again. Right. Yes. Yes. So every time you go to even higher energy, then this peak and trough, it increases. So that means that you will be able to see with more and more probability. So so let's say that I claim that both me and my body will see the electron with 50 and 50% probability. So that means if an electron is there, then half of the chance is that I will see it, half of the chance is that my body will see it. Okay. So this is the another idea that was very revolutionary. And you know what? When people first came up with the idea of wave particle duality, and eventually in 1926, Schrodinger, he proposed his idea of describing the wave and particle nature of electrons, he still didn't understand that the simple question when I asked that if I and my body, they take their position in two different places, which one is going to see the electron? He couldn't answer this. It was actually answered by a person. His name is, I think, Max Born. So Max Born, in one of his book, he wrote this comment in the margin of the book, or in the footnote of the book. He said that the square of psi indicates the probability of finding the particle. And then the whole world, they actually recognize that, oh, this is the meaning of a particle and the probability of seeing the particle. Okay. And then the idea actually became popular that if you want to discover the particle, you have to take the square of psi, and the square of psi will tell you the probability. So before that, people didn't understand. And just imagine that this guy, Max Born, he thought that it is so simple that we don't need to write anything about it, just put it in the footnote. So people are that crazy. Yes. So yeah, I mean, the whole um, quantum world is so strange. It takes a lot of time to really understand and get habituated with it. So, all right, I think we are top of the tower. Let us wrap up together, and we'll continue our discussion from next class. Thank you, guys.